Hello there. In this video, we're going to watch a video on properties of exponents. And this is, I like to think of order of operations for kind of the higher level exponents. So we have to think about adding and subtracting and dividing and multiplying exponents together. So we'll start with a basic principle. We'll start with x squared times x cubed. And we'll keep the bases the same because this is important. I want to write out what I know about this expression if I'm going to know how I can, or even if I can, combine these terms. So I know that x squared is just x times x. And then I know that x cubed is x times x times x. And I have to think about how I know this. I know this because exponents are just repeated multiplication. So x squared means I'm taking an x and multiplying it by itself twice. And then x cubed means I'm taking x and multiplying it by itself 3 times. But if my goal is to simplify this down, I have to look at what I have here and think about how many total x's I have. I have a total of 5, which means I can rewrite this as an x to the 5th. Now the question is, do we want to be responsible for expanding and then contracting back down every time we want to do this problem? No, this is where the shortcuts come from. And this is where we can see that, 5 happens to be 2 plus 3. And so we get ourselves a little bit of a rule. And so the rule, which I will put in this column over here, is that when we have two bases, x to the a times x to the b, this will equal x to the power of a plus b. We add the exponents when we're multiplying their bases. Okay, great. We have a rule where we can add exponents. So we have a rule where we can subtract exponents. Well, let's look at the example. X to the 5th divided by x cubed. We'll expand it similarly. So take x times x times x 5 times, and then in the denominator, x times x times x. So what do we do with this? Well, I have to remind myself that division is just the operation of undoing multiplication, and all I've got here are multiplications. So if I look at it, I can cancel one of these x's in the top and bottom. I'm multiplying and dividing those two out. That simplifies things. What about here? And here? But now I've gotten to a point where I have nothing left in the denominator. I just have x squared in the numerator. And now I can notice that 2 is equal to 5 minus 3. So this leaves us with a rule that x to the power of a divided by x to the power of b equals x to the power of a minus b. Okay, great. If we're multiplying bases, we're adding their exponents, and if I'm dividing their bases, then I am subtracting their exponents. So this leaves me with some nice rules. Well, what about, let's take a look at the expression, x cubed to the 4th. Now, really quick fast forward to expand this expression. Okay, so like we did with the addition property, I can look and see how many do I have in total. And I have 12 in total. So this means that I have x to the 12th power. And I can notice that 12 is equal to 3 times 4. And so this leaves us with the property x to the power of a, all that to the power of b, is equal to x to the power of a times b. And we can expand this rule. Say I've got two different bases. I've got x to the power of a times y to the power of b, and all that to the c power. Well, there's nothing I can do about combining x and y because they're not like bases. This only can happen when I have like bases, but I can still take this c and distribute it to each expression, which means x is now to the power of a times c, and y is to the power of b times c. Okay, great. I can exponents, I can subtract exponents, I can multiply. Can I divide? Let's take a look at the idea of x to the 1/2. X to the 1/2 is simply the square root of x. Now, when we have radicals, we have the cube root of x, we have, say, the 4th root of x. These numbers right here are what are called indices, or the index of the radical. But with square root, we don't write one. That's because it's automatically assumed to be 2. This is like when we have x, we can look at that as 1x. We don't write the 1, but we assume the 1 is there. In this case, we assume the 2 to be there. We can also write this as 1x to the 1st. Again, not an exponent we usually write out, but also something we automatically assume is there. So this means the cube root of x is x to the 1/3. The 4th root of x is x to the 1/4. And if we, say, make it a little bit more complicated, let's say the 4th root of x to the 5th would be the same as this exponent here is the numerator of the rational exponent, and the index is the denominator. And then we get into a slightly more complicated example, like square root of x squared. And I know what you're thinking, cancel the x, cancel the square root. Well, if we double check this, it looks like it checks out. 2 divided by 2, which can be simplified to be x to the 1, which is just x. We run into a little bit of a complication when we consider that when we're squaring something and then square rooting something, we could be dealing with positive or negative solutions for this exponent. So really what we're supposed to say is this is equal to the absolute value of x. So keep that in your back pocket. It won't come up the rest of this video, but keep that in mind as we move throughout this. All right, so we can add, we can subtract, we can multiply, we can divide. We can take positive exponents. I mean, we know what 2 squared means. It means 2 times 2. What about an idea of x to the power of 0? What do we do there? Can exponents be 0? Well, let's look at what we do know about exponents. Let's write an expression. I'm just going to use a base of 2. Let's say 2 to the 1st. Well, anything to the 1st power is itself. That's just 2. 2 squared. Well, that's 2 times 2, which is 4. Okay. Do one more. 2 cubed is 2 times 2 times 2. This would be 8. And notice each time we're multiplying by 2. Of course we are. That's what exponentiation is, repeated multiplication. And so if the exponent's going up by 1, then that means the number of times we're multiplying is increasing. So we would want to know what would 2 to the 0 be. Well, if I'm going back the other way, if I'm decreasing my exponent by 1, then that would assume that I'm dividing by 2, right? That seems like a safe assumption. So I have to ask myself, what is 2 divided by 2? And it is equal to 1. And you can do this with any base. We can try it with 3. 3 to the 1 is 3. 3 squared is 9. 3 cubed is 27. However, when I go back 1, I'm dividing by 3. Okay? So do it one more time. Divide by 3 to get 3 to the 0. And 3 divided by 3 is equal to 1. So x to the power of 0 is equal to 1. Now, it seems like a good time to talk about what are our bases. I mean, does it matter? And the answer is yes, it does. Take something like negative 2 squared. That'd be 4. What about negative 2 cubed? That'd be negative 8. Okay, I don't know why I put it in parentheses. Negative 2 to the 4th. That'd be positive 16. So we can see an alternating pattern of positives and negatives. When we get into functions, this is going to create a bit of more of a problem. So we're not going to be dealing with negative bases. In this specific case, the properties still do hold. But we're not going to be talking about negative bases a lot in the future. It's just something we're not going to do. What about 0 as a base? Well, 0 to the power of 1 is 0. 0 squared is 0 times 0, which is 0. And anything times 0 is 0. So we're just going to keep this repeated pattern. So we get to the point of, what do we say when we've got 0 to the power of 0? Well, if we follow our same pattern going back one, I'm going to have to divide by 0. But remember the rule that we cannot divide by 0. So this is undefined. What's more is if I have, building on this idea of 0 to the power of 0, anything to the power of 0 that we've established is 1. So if I'm dividing by 1, now this we could probably do. This makes sense. 1 divided by 1 is 1, so 0 to the power of 0 is 1. But we've got two rules in competition here. Anything to the power of 0 is 1, but 0 to the power of anything is 0. So for that reason, I will not be defining this. There are limit problems where we can find out that 0 to the power of 0 approaches 1, but that's another video for another time. So all this, suffice it to say, is with all these rules, x does not equal 0. Now, for 0 to the power of 0, it's a computational issue. But if we had 0 squared times 0 to the third, we could apply our addition rule and say 0 to the power of 5. But that's 0, and no matter what we do, it's boring. So sometimes it works out, sometimes it doesn't, and we're just not going to be dealing with 0 as a base for anything. Okay, so we've got an addition, we've got a subtraction, multiplication, division. We've got a rule for if the exponent is 0. What about x to the negative 1? Well, this becomes a little bit easier. I mean, how can you repeat multiplication by itself negative 1 times? But if we follow the pattern that we have established with these 2's, negative 1, going backwards and decreasing the power means we divide by 2. So that means this is 1 divided by 2. That's just 1/2. Now squeeze in one more, 2 to the negative 2. Well, that'd be 1 over 2 squared, which is 1 over 4. So this gives us an extra rule that x, I'm going to start on a new sheet, to the power of negative a is equal to a fraction of 1 over that base, but we can then make the exponent a positive. And it just goes to show you that no matter how we write the problem, we can always write the answer with a positive exponent. And this also does extend to what if the negative exponent is in the denominator? Well, this would just be 1 over x to the a. And using our fraction rules, we just take the reciprocal of this, which is just x to the a. So we've got negative exponents. So what about some examples? Well, I'm going to leave that for the next video. If you like this video, please like and subscribe, and feel free to leave a comment, and I'll see you for the next video. Thanks for watching.